I'm Dennis Lettenmeyer. I'm president of the hydrology section, and I want to welcome all of you to the 18th Langbein lecture. This year's lecture is being given by Bill Xray of the University of North Carolina. It would take me some time to go through all of Bill's accomplishments, and I won't take your time doing that, but I will just mention that Bill has a BS in chemical engineering at UC Davis, an MA in chemical engineering and PhD in chemical engineering at Princeton University. He was on the faculty at Princeton University from 1975 through 84. From 1984 through 95, he was at the University of Notre Dame, where he was the chair for some years. And since July 2003, he's been a professor of environmental sciences and engineering at UNC. The topic of Bill's Langbein lecture is opportunities for impacting the trajectory of hydrologic model development. Bill will have about an hour for the talk, and then we will entertain some questions thereafter. Bill?
Thank you, Dennis. When I was first contacted about this talk, it was in August, and I was traveling, and Dennis sent me an email and tracked me down. And I was really pleased to hear that I'd been selected to give this talk, and Dennis asked if I'd be willing to do it, and I said, yes, I would. And then I waited, and I thought I would get an email saying, well, this talk is supposed to encompass certain features. And I continued to wait, and I'm still waiting. What I did get was an email from AGU, and it said, your title and abstract are due September 1st. And so I did what most of you probably do, is try to come up with a title that I thought might match the talk 3 months later, and also an abstract that was broad enough that I could fit something in that would make sense. So I hope I was able to do this, and I thank you all for coming today. I know that they have to cancel all of the other hydrology sections to get you to come to my talk, but I do appreciate that you did do this, and I hope that it will be a worthwhile time for you. I'd like to point out in the lower part of the slide the logo for the University of North Carolina, and I believe it's the only university that has as its logo a water well, so it's quite appropriate that it be included. So after not getting any information about this talk, I looked online to try and get an idea of what I should do, and I saw this description of the Walter Langbein lecture. And it says it's given at the fall meeting, and it's awarded for lifetime contributions to the basic science of hydrology and for unselfish service promoting cooperation in hydrologic research. There were two aspects of this that really struck me. One was lifetime contributions, and the other is promoting cooperation. So I thought about those for a while. The first is lifetime contributions. And I have a policy with my students that when they refer to me, they should refer to me as their former advisor, not their old advisor. And I think with this talk that I have to concede that they can now call me their old advisor if they choose to do so. So that's the first feature of this talk. The second is in promoting cooperation. And I said to my wife, who has been my greatest supporter for 40 years now, I said, well, this is really something that I have to be careful, because they're going to webcast this and they're going to archive it. So I have to be very careful that I don't insult anybody, because it'll be there forever. And she turned to me and said, pretty tempting, isn't it? So I've still adopted the plan that I would try not to insult anyone. So I had some further considerations about this talk, and I spent some time trying to look up different features of it. And one thing that's very clear is that it exploits the good name of Walter Langbein. If I were to rent a room across the street and say I'm going to give a lecture, there would not be this many people there, even if I gave away pizza. So you're here in large part because of Walter Langbein and the contributions that he made to our profession. The other thing is that the people in this room have a much broader spectrum of knowledge than I do. And many of you have probably very little interest in the kinds of things that I do. And so I have to be somewhat sensitive to that. So you're not going to be interested in the details of my research, and I decided that this lecture would not then consider the details. I would try and consider some general things and some items that are consistent with the overall thrust of the Walter Langbein lecture. I hope I will give you some fodder for thought, not just tell you some things that I think are the way they are, but rather give you some things that you can think about and decide that might be worth considering further. In line with the two major features of this talk, since it asks for lifetime contributions, I think it asks for some perspective. So I'm going to give you some perspective, some of the experiences that I had in the time that I've been working, and also the idea of promoting cooperation suggests that there be some issues talked about that are of community interest and for consideration by the community as a whole. So this is what I'm going to try and do. And in order to do that, I have this as my outline. When I started, I worked with some tidal models in the 60s, or starting in the 70s, my work was, until the 80s, and I'll give you some details of that experience. Then I want to offer some thoughts on deterministic porous media models, because I've been working more in that in recent times. I am then going to tell you some of the details of my most recent work, which is the thermodynamically constrained averaging theory. I'm going to try to avoid many of the details and equations just to give you a flavor of why we're trying to work on this. I'm going to then talk about some considerations that may be useful in developing models, and then have some acknowledgements. So first of all is the tidal models from the late 1960s to the early 1980s. So I started to work on tidal models in about 1974 when George Pinder got me involved in doing this. And one of the best reports that was available at the time was a model of this region of the North Sea, this little western region, which you can see has this kind of unusual shape. At the time, the models that were being used were finite difference models. And this particular model had even space nodes. You can see that it was a square grid, and they had approximately 1,700 nodes. So this just gives you some perspective for those of you that were not alive when I started, the way things were at that time and the size of the models, and maybe we take for granted the much larger ones. So if you remember, 1967, about 1,700 nodes. So what I was asked to do was to try and see if finite elements would be a useful method instead for modeling these kinds of regions. And we were asked to look at a system that looks something like this. It's an irregularly shaped region. There's a no flow boundary on it. There's a seawall there, and you can see there's a river inflow and another tidal region. And these were the main features that were of interest. And we were asked to try and model the circulation in that region. And one of the other challenges was to impose boundary conditions. So if you take a region like this and you put a finite difference grid on it, you can see that it's difficult to match the geometry. In particular, in this diagram at the top, there's just a lack of connection with that shape. Also on the right side, on that diagonal region, you can see that it stair steps down. And it's hard to match that kind of geometry. So the reason for going to finite elements was to try and match the geometry of the system we're interested in, to put more nodes where we had the most interest, and also to see if we could use an irregular grid. So one of the shapes that we tried was using these quadratic elements. And you can see that it's difficult to fill the space with elements of this size when they have to line up. The nice feature is it has curved geometry, so we were able to match some parts of the boundaries. These were higher order in space, second order, and that was one approach. Another was to use triangles, and they were easier to fill the space with, but it was a lower order accuracy. So I started to do this, and I worked on this for about 2 months. And I had to go down and report to the people that were funding this work. And I went to meet with one of the scientists who had been doing the finite difference modeling of these regions. And he wanted to see what I had. So I showed him my diagrams, and I had arrows on the sides of this region where there would be a little bit of flow leaving the region despite the fact that it was a no-flow boundary. Now, on average, there was no flow leaving, but at certain points, the flow velocity wasn't exactly zero. And that was a result of the way the finite element method worked. And so I showed him this and showed him how things are working, and he was thrilled. And I was, why are you so happy? This isn't working as we'd like. He said, well, I have spent a lot of years developing pre-processing and post-processing software that works on square grids. So if you have something that doesn't work on square grids, that works on other grids, then all of my stuff has to be thrown out. So he was really hoping that this wouldn't work because he was really happy with the technology that he had. So as we went on into the 80s, Dan Lynch did a review, one of those reviews, and in the period of 79 to 82, now remember when I started with this, I told you the finite difference model was 67, and then I did some stuff in 74. So he said at this point even, which is many years later, he talks about finite element models being potentially operationally useful, and that the advances may allow the finite element technique to reach its oft-stated potential. So it's not a ringing endorsement of the method after these many years of trying to work on it. And we had done some work then even a little later in 1984. We had a quadratic grid that looked like this, which now we're up to 265 nodes, as opposed to the 1,700 finite difference nodes that they did in 1967. And then 3 years later, we had a bigger region, and we were all the way up to 990 nodes and could do some simulations. So you can see that the development of these things was very slow. And it was a real change in the technology. It took a lot of effort. It took a lot of time. And the results were still kind of talking about the potential that this was going to work out. So what I can say about this in context of modeling is that significant advances were based on regular grids in the finite difference context. They had really good models at that point. The implementation of the finite element models caused the quality of modeling to go down. And we were not able to do what the finite difference people were able to do, and that decrease in quality persisted for more than a decade. We were just kind of trying to get caught up. The final successful implementation of finite elements required a reformulation of the mass conservation equation into a wave equation form, and it's what's used pretty much in models that are known as QUADI and ADCIRC, which are used today to model large regions. The subsequent developments have led to truly remarkable capabilities using the unstructured grids and advanced computer architecture. People now have millions of nodes. They do three-dimensional models. Someone was telling me yesterday they're hooking together these coastal models with ocean models. And this work it's really, the finite elements have overcome many of the issues, and they've really supplanted using regular meshes in model region. But it took a long time to get there. So the next topic or point that I'd like to talk about is some considerations for deterministic porous media models. It seems like it's a different kind of a topic. It is somewhat. I'll try and tie these together later on. In modeling porous media, I think that the overwhelming challenge is scale. We have to try and look at these systems at a variety of scales and try and understand how the systems behave. The other feature is that the foundation for porous media analysis really rests in experimental observations. People have built equations by curve-fitting data and trying to say that this seems to represent the process pretty well. I want to talk about the different scales that are involved here. The microscale is the continuum scale where you have identifiable phases, interfaces, and common curves. So here we have, in this diagram, we have a region that's a solid phase. We can have a fluid that's a wetting phase. It's one of two fluids that preferentially wets the solids. And we can have another fluid phase which is a non-wetting phase. Now, in addition to that, we have interfaces between the fluids and the solids, which are indicated here, and there are also interfaces between the fluids. So at the microscale, we have all of these separate regions that we want to be able to look at and quantify and describe. There are also common curves, which are the locations where three phases come together. So we have to deal with all of that. Now, at the macro scale, it's still a continuum scale, but instead of looking at the phases and the interfaces and common curves separately, we talk about how the relative amounts of each of these in a particular region. So we would take a region such as this, and that would be a macro scale. We talk about 30% one fluid, 20% another fluid, 50% solid, something like that. But they're all present together rather than next to each other. So the needs that we have in order to be able to model these things are consistent transformations between the scales. We need relationships between measured and modeled variables, and that's not always easy to come by those. And we need a consistent description of the important processes at each scale. When I started to work on this, it was shortly after, I guess, Jacob Behr had come up with this REV idea, and Jacob Behr is the Horton medalist this year. The idea of the representative elementary volume, and it's a minimum volume of a sample for which parameters and variables are independent of the volume length scale. So for a porous medium, it has this implications, that if we plot the variable versus the length scale, if we make measurements at a really small scale, at this micro scale, we'll see that the variable comes out to have quite a variation in its values. So if anyone were to go and make a measurement at that scale, they would have to also provide the length scale at which they do the measurement. With the REV concept, we then have an intermediate scale, a macro scale, where the variable value is fairly constant. This means that we can take derivatives of it in space and come up with reasonable values, and we can talk about quantities such as density and velocity, and we can all be talking about the same thing. At the larger scale, when the system heterogeneity comes into play, we can't really account for the variation in space, and the best way to model that is to look at the system as a whole. We can look at its maybe time variation, but not the spatial variation. So the REV has a number of drawbacks. One is that it has to be independent of space and time in the formulation of equations. All of the variables that we consider have to be at the same scale. So these are properties of phases and properties of interfaces, all have to be considered at the same scale. The definition of each larger scale variable has to be consistent and explicit when it's written in terms of the microscale variables that it derives from. And this is important if we're going to make connections between scales. And the mathematically defined larger variables and equations have to be considered in light of measurements. And it's tough, as I said, to make sure that we have variables which we can define mathematically and also know that we can measure them in some kind of physical way. So when I started to do this, I thought, well, once we get to the macro scale, we're home free. We don't have to look at the micro scale anymore. And as usual, I was wrong. It turns out that there's been a lot of pretty interesting work done to look at this very small scale. One of these approaches was by Carlo Montemagno, and he developed this photoluminescent volumetric imaging, whereby he took a sample, and the sample was composed of optically index-matched fluids and solids, so it was glass with optically index-matched fluid, and doped the interface and was able to come up with configuration of the phases and the interfaces between, so that we could look at these values and then try and take that data and scale it up to the larger scale. And this cutout is about, I think it's 5 millimeters on the side. So it's a pretty small sample that he could look at. He also did it for multi-phase systems, 2 fluids and a solid, and could analyze the volume fractions and also the areas that could be looked at. There's also work being done on Xray Tomography, and Dorota Wildenschild and her group are working on this. Here they can measure the equilibrium configuration and saturations, and this is a diagram based on some spherical grains, and you can see cutaways of the different fluids. So by looking at this information at the very small scale, we hope to be able to inform what's going on at the larger scale. So it isn't just that the macro scale can handle it. So the question I have is, are we able to gain new insights and understandings? So I'll tell you about 2 incidents that have contributed to the way I think about these things. I did a paper with Kevin O'Neill, and we tried to develop Darcys Law. We started out, we had the microscale momentum equation, and we had Darcys Law. And what we wanted to do was connect the two, see if we could go from the small scale to the larger scale. So I think this is kind of target science. We said, this is the result we want to get. Can we hit that target? So what we did was we used averaging theory, and we were able to make assumptions and make the whole process move along so we could go from a microscale momentum equation to getting Darcys Law. And we were pretty happy with that, and I thought, well, this is a reasonable way to proceed. So then, a few years later, I think it was 1983, roughly, just to give you a time frame, I was having a phone conversation with Rien van Genooten, and I have really no recollection at all what the conversation was about. But at the end, as he was about to hang up, he said, Bill, are you still working on that averaging theory? And I said, oh yeah, we're still working on it. He said, did you get any results yet? And I said, well, we can get Darcys Law and we can get equations of transport. And he said, yeah, but did you get anything new? And I said, well, no, we didn't. But it was an eye-opener because it meant that we really have to proceed this way. We want to start with microscale conservation equations. We want to apply the averaging theory, and we don't want to have a target at the other end. We want to see what happens. We want to come up with appropriate relations, whatever they are. If they happen to be what people are using and what everybody knows to be true, great. If it turns out differently, okay, then we have more work to do. And to me, this was a real insight on trying to make sure that what we're developing really is scientifically sound, not just scientifically historic. So computing power and techniques have really been revolutionized over the last 50 years, but the equations that we're using, the basic theory, is essentially unchanged for a very long time. The solutions of the governing equations are certainly more accurate, but if we're really going to be improving the way we model systems, we have to do more than just upgrade the computer power. False information, often repeated, becomes truth. And I think there are a number of things that we do and we say, well, everybody knows this to be true. And if everybody didn't know it, we would be a lot better off because we would question it a bit more. So the use of equations and variables without really knowing where they come from, without knowing their origins, can lead to erroneous truths. And we have to make sure we have consistent definitions of variables across scale. In part, this is because of the development of their ability to model systems or to monitor systems at very small scales, and then we want to be able to tie that onto what we do at larger scales. And also we have to know what our measurements at larger scales really imply. So these are the observations I have on that. So in an attempt to do this a little bit better, I want to talk to you briefly about this thermodynamically constrained averaging theory, which is what Casey Miller and I have been working on for, I guess, 10 years roughly now, to try and come up with a really systematic way of doing things. I'm going to give you a few details and show you a couple of things that we have found, and hopefully it'll be interesting to you. So the approach, first I'm going to describe it. The idea is that we formulate conservation equations and thermodynamic relations at the small scale. And we do this for phases, interfaces, common curves, and common points. Yes, we have a lot of equations because there's lots of phases, interfaces, common curves, and common points. And then we use some theorems that allow us to change the scale. We get up to a larger scale, we can move up to the macro scale, or we can move up to the mega scale, and we have a consistent way of making that transformation. We then use the entropy inequality, and we constrain it with the conservation equations, and this helps us to define the entities that we're going to model, the different phases and interfaces, and also the processes that we want to model. We then end up with the need to come up with some closure relations, some constitutive equations, and we come up with these by requiring that the irreversible processes that occur within the system produce entropy. And finally, we develop some additional constraints that arise because of the change of scale. There are some quantities that come into play that weren't there previously. So this is the idea, and I'm going to show you what it is by a diagram. So we start off with the microscale entropy inequality and the microscale conservation equation. What we do with this TCAT method, which is different, is that we also have microscale thermodynamic equations and microscale equilibrium conditions. And we have averaging theorems, and we take these averaging theorems and apply them to all of these microscale equations, and therefore convert everything to this larger scale. So we have a larger scale entropy and conservation equations, and also larger scale thermodynamic relations and equilibrium conditions. So once we have these, we mush them all together, and we come up with an entropy inequality which is constrained by the fact that it also must satisfy the conservation equations. We try and simplify this and come up with some approximate closure relations. So everything up to the light blue box on the top is just turning the crank. After that, to the darker colors of blue, there's some approximations that have to come into play. So we then end up with some closed parameterized models, and we can use subscale information, modeling, and experimental data to help us get values for the parameters in that model. We're still a little bit short of information. We need these extra equations, these evolution equations, and we use the averaging theorems to come up with the evolution equations. So at this point, these two things are what we have. It's our complete set of equations. Now, how is this different from the usual approach? The usual approach doesn't involve averaging of the thermodynamic relations. So if we cut those out and don't apply averaging, we just have the microscale conditions kind of blowing in the wind, and they become a separate set of conditions which are not necessarily satisfied when we look at just formulating the thermodynamics at the larger scale. So we believe it's important to keep that all tied in together. So I'm going to have to give a little bit of notation here, so hopefully we can get through this. I have a subscript is always going to define a microscale variable, and a superscript is going to denote a larger scale macroscale variable. So if we have a quantity F sub W, that would be a microscale property of the W phase, we can average it to a larger scale. And the general expression for an average looks like this. We take the microscale value and integrate it over some domain. We use a weighting function m if we want to, and then divide by that weighting function integrated over perhaps some other domain. So that's a general average. We can use that to define all the other averages we use. We won't be using the full general form. This is the part of the general average that you might want to look at. We also have what we call an intrinsic average, which is just a function integrated over the domain where it's defined, a property of the wetting phase averaged over the wetting phase. So it would be denoted this way with a superscript W to indicate it's a macroscale variable. We also have density weighted averages that come into play. So because they come into play often enough, we have a separate symbol for them. We have the superscript with an overbar on it. And so that is the density weighted average. So we have those three averages. We have another average we need to worry about. Sometimes we have a property of a phase, and we're going to average it over the interface. So just over the boundary of the domain. So that's denoted this way with a subscript to indicate it as the region in which it has a microscale value, and the superscript which indicates the region of integration. So we can also have variables that are properties of interfaces, like a wetting phase solid interface here, and that's denoted in this manner with just the superscript WS, so that's consistent with the intrinsic average idea for a phase. And we also have density weighted averages of interface properties. So these we can move up. I just got to tuck in one more here. We have some variable, and sometimes the averages are not just direct averages. They are combinations of averages of other quantities, and we denote those with 2 overbars. So we basically have these 7 different kinds of averages that may appear. Just remember, the superscript is the larger scale, subscript is the small scale. The bar means it's a density weighted average, and the double bar means I have to tell you more. So hopefully that we can keep that straight and get through some of this pretty well. So the usual approach to larger scale thermodynamics is to posit the thermodynamics at that scale and then use what's called a rational thermodynamics approach to get the dependence of the different functions on the macroscale quantities. There are some disadvantages to this. One is that the precisely defined notions of equilibrium thermodynamics are merely assumed. So we've gone into another regime by not including the microscale thermodynamic parts. Quantities such as absolute temperature and entropy are considered to be primitive concepts, but they really don't have a precise physical interpretation. So this begins to provide a divide between the math and the physics, and we really need to try and preserve that if we're going to be able to make good gains. The presumed functional dependence on an expanded variable set that we would use at the larger scale is sometimes inconsistent with what equilibrium thermodynamics shows, but it sometimes can be essential to the theory. So we have to make things that are physically inconsistent in order to make things mathematically consistent. So that's a bit of a problem. It's an elegant mathematical approach. It works in some cases, but it can lose touch with the ability to obtain correspondence with physical measurements. So if instead, using TCAT, we make use of the established thermodynamic formalisms and integrate those to the larger scale, we can make some headway. So as an example, if I show you some single-phase thermodynamics, I just want to show you what happens to the thermodynamic expressions. So we start out at the microscale. The classical irreversible thermodynamic formulation tells us that the energy per volume is related to the temperature, and the entropy per volume, the pressure, the density, and the chemical potential. These are all subscripted. They're all microscale quantities. So if we take the material derivative of this, using classical irreversible thermodynamics, we get these material derivative that looks like that, and we also get a Gibbs-Duhem equation that looks like that. So this is the microscale form. So we can integrate the microscale form and come up with a macroscale expression, which is here. I've just averaged all the terms in the expression for energy by integrating over the phase. Now I'm adding and subtracting some undefined large macroscale variable to each of the terms so that we have no products of microscale variables remaining directly there in terms of deviations. So by doing this, we can then average and evaluate the integrals in the top line of this equation because they're products of large scale and small scale variables. So if we evaluate those integrals, we get a form that looks like this. So the energy is related as it's shown, and then it has the second line, which is these deviation terms. But if you look at the first line, it looks a lot like what we had at the microscale. So that's kind of good, and if we're into this target mentality, we might say that's fine. But what about the second line? What can we do with this second line of variables? And the idea is that it would be nice to set them all, deal with them, and make them equal to 0. If we can make them equal to 0, then the macroscale energy looks like the microscale energy. So that's what we want to do. We want to target it and make that happen. There's a lot of ways to do it because we have freedom to define these macroscale intensive variables, the temperature, pressure, and potential. So one way is to make each of these residual terms go to 0. So if we do that, target each of them to 0, that provides us with the definition of the largest scale variable that we're going to use. So we have that the temperature is just an entropy-weighted average of the microscale temperature. The pressure is just a volume-averaged pressure. And the chemical potential is a density-weighted chemical potential. That's one possible set. There's a second option, which would be maybe to set the first term involving the temperatures to 0 and have the other two together be equal to 0. If we adopt this approach, the first one tells us that the macroscale temperature that we're using is an entropy-weighted macroscale temperature, and the second one tells us that there has to be a relationship between the chemical potential and the pressure. The thing that's important to understand is that when we go from the microscale to the larger scale, these variables, temperature, pressure, and chemical potential, lose some of their fundamental meaning. So it's very important to make sure we know how we're averaging them and what values we're going to use. And the reason that's important is because it's the gradients of these variables which end up impacting transport processes. So we have to know what we're working with. So if we do this, and even if we zero these things out, so we've done the integration of the microscale energy to the macroscale, and we have this form for the energy equation. Still, when we differentiate it, we get extra terms beyond the microscale. We have this part, which is what we would expect based on the microscale form, but we also have these derivatives of deviation terms. And these deviation terms cannot be eliminated by judicious selection of the definitions of the largest scale variables. So we have to carry them around. So what we can say is that the definitions of average temperature, pressure, and chemical potential depend on the targets that we select, how we want to define them. It's important to know the relationship between the macroscale and microscale variables in order to have meaningful models. The gradients of these macroscale intensive variables are what give rise to macroscale fluxes. And when we get to larger and larger scales, the value of these integrated parameters becomes less and less because they average over so many different degrees of variability. So we have to be pretty careful about this. And I'll show you an example where you can get into a little bit of trouble. If we look at the microscale hydrostatic pressure distribution in the fluid phase, this is about as simple as we can get. We know that del P minus rho G is equal to 0. So if we average this, we come up with a macroscale hydrostatic pressure distribution in the fluid that has this form. So you'll see that there is the initial part and then there's this integral part. So the question is it possible to target the general macroscale pressure so that we don't have the integral term? So what we'd like to do is make that integral term be equal to 0. And if we do that, then you can see we have this nice relationship at the larger scale that del P minus rho G is equal to 0. And that's something that people really kind of like to have, because we say that the Darcy velocity is proportional to del P minus rho G, and so at equilibrium that should be 0. Can we really do that? So if we go and try and target this thing, you'll see that it doesn't always hit the target. The problem is that in general we can't make that kind of a definition. That function doesn't always exist. So in some instances we have to use a different definition. So there are reasons not to require that the macroscale pressure distribution satisfies this form. One is this function doesn't exist for all cases. In fact, when the density is not a constant, you can't get this at the macro scale. It seems kind of surprising, but if you go through the math, that indeed is the way it works out. Any pressure that we have at the macro scale should be physically meaningful in terms of and written in terms of well-defined microscale quantities. It needs to exist, and we should be able to use it from system to system. There's an effort sometimes to declare a particular one of these functions to be the macroscale pressure. Can't be justified. And the same thing can be said for temperature, which has implications in climate change, and the same thing can be said in terms of chemical potential. There isn't one way to average and come up with a particular value that's the definitive one. Also, if we select a way to define a variable based on the aesthetics of one equation, it really ignores the fact that the quantity has to be used in other equations, and the aesthetics there may not be quite as good. So another region or example where this is important is in the definition of capillary pressure. So the definition of capillary pressure is that it's equal to the interfacial tension times the curvature. This is at an interface at the microscale. At equilibrium, it's also equal to the pressure distribution, pressure difference at the interface. Not in the phases, but at the interface. So we know that at the microscale. So when we go to the larger scale, we have these forms of capillary pressure, and we try and plot it as a function of saturation. And the form that's generally used at equilibrium is that capillary pressure as a function of saturation is equal to the average of the pressures in the phases, the difference of those averages. So we have an equilibrium relation, and we have pressures that are averaged over the phases, not pressures that are evaluated at the interface. So if we extend this and recognize that making PC as a function of saturation is in large part an attempt to make it a function of interfacial curvature at the larger scale. So what we can do to try and do a better job of accounting for interfacial curvature is to make it a function of saturation and also of the amount of area per volume. And this is what's done, and we get an expression like this. And there's been some work going on to try and come up with this relation at equilibrium. There's also some work that's being done to come up with a dynamic condition. It says, well, the capillary pressure is only equal to that pressure difference at equilibrium, so we really should look at the change in saturation that's occurring as this thing relaxes to equilibrium. Now, there's some figures, and these again were produced by Dorda Wildenschild and Katie Culligan, where if you look at the top and bottom of each pair of figures, these are at roughly the same saturations, 0.13, 0.15 on the left, and 0.59, 0.61 on the right. So the saturations are the same, but the distributions of the fluids are different. And the amount of interfacial area between the fluid phases is different, even though the saturations are the same. Now, if we transform from one to the other, the saturation wouldn't be changing, but the interfacial area per volume would be changing. And it seems that that rate of change of interfacial area per volume would also be something that would need to be taken into account. So if we go back to this form that we have at the bottom, we don't have that rate of change of interfacial area per volume. We have these volume average pressures. If we base this instead on the TCAT method, we come up with a more complete equation. And it's not just a longer equation. It's an equation that has more physical insight in it, I think. It has a term that accounts for the relaxation of the interfacial area per volume to its equilibrium form. It also has the pressures being averaged over the interfaces, so they're surface average. Now you can take those and say, well, yeah, I can't measure that, I have to do something else, and that's okay. But at least we know that this is the form that is more general, and we have an understanding then of the approximations that we're going to be using in our equations. We also need an equation of evolution for the geometric densities, and these are the amounts of interfacial area per volume and the saturation. So we need equations for that. These quantities don't exist at the microscale, and so we have to come up with equations. Now, the equations that describe these are not conservation equations. They're distinct. They really are mathematical expressions that relate to geometry changes. And we can get these equations by using the averaging theorems directly. And we have a form at the bottom which maybe you can't see it, unfortunately, but it relates the area per volume to the saturation change and also the relaxation of the system to equilibrium. And this is another equation that's needed to close the system. Okay. So if we look at the TCAT approach and the rational thermodynamics approach, there's a number of different variables that come into play. We have a surface stress tensor, interface velocity, and so forth. You can see the list down the left. In both formulations, you can put in check marks and say, oh, we have those. We get those. So it's okay. You can use either one. But if we look at the approximations that appear, you'll see that the surface stress tensor, for instance, it doesn't take into account any orientation of the interfaces if you use the rational thermodynamics approach. The velocity of the interface is proportional to the gradient in the interfacial area with the rational thermodynamics approach, which is not right, because that would mean at equilibrium you couldn't have a gradient in interfacial area. So we have these two differences. So rather than go through each of them in detail here, I'll just show you that using the rational thermodynamics approach, we have some that are expressions that are fatally flawed. The surface stress tensor, the interface velocity, the interface mass density, and the evolution equations. They don't work. We just have no chance. So we can't use that. We have to get rid of it. Now we have some more quantities, the stress on the solid surface, and things are not so bad here, because in some very specific and simple situations, we can get approximations that work, but we can't come up with the BO coefficient for the solid. And we have been able to come up with some data that shows that we get a great match with the data in concrete using the TCAT approach, whereas the other approach misses it at the low saturations. So I propose that we're going to throw that out as well. And what we have to do then is just use this approach, and now we have the equations that work, and we have some which we have to make approximations about. But this lets us get to a set of equations which model the system. They're perhaps complicated equations. They reduce to simpler forms, but then we know the assumptions that we must make to get to simpler forms. And we can then develop our science in a systematic way so that we can really make good advances when we do our modeling. So I would like to now kind of go off and do some things on considerations for model development. just some things, and I have to apologize. There's a book by Christensen called The Innovator's Dilemma. It's a business book, and it has to do with reasons that businesses have failed. And I looked at this and I thought, well, it kind of relates to the work that we do in science and our efforts to come up with better models. So I'd like to kind of force our science into this context. We're looking at performance versus time. Now, when we're trying to model a system, we may have some performance that's required at the low end. We have a relatively simple system. We want to be able to model it. And we also have really complicated problems that we want to be able to model. And in between the two, we have the full range of problems of interest. We want to be able to model these. How do we go about doing this? Well, we start out usually with models that don't do such a great job, and we make changes to our models. And by the way, I'm not meaning to imply that any of this is linear. This is just a schematic. But our models with incremental changes, we begin to do better, and we can then show that we're able to model some of the low-end problems. But you'll see as we make headway into more complicated issues, we may not really be gaining on the complexity of problems. As we understand the physics and the biology of what's going on, the problems become harder, and we just really can't approach them with the methods that we're using. So what happens sometimes is we go along, and then we have a disruptive innovation. And we put in an innovation, and it really degrades our ability to model. Someone puts in something like finite elements and says, well, now I'm going to use that. Well, okay, that's fine, but now I can't model the system anymore because the method doesn't work. And so, or the equations become more difficult, and so now it becomes harder. I have to develop more coding and get more data, and it becomes difficult. But if we persist, if it's a truly disruptive innovation, we will improve our ability to understand and model things such that we can make gains on the more complex problems. But it requires us to be willing to back off and say, well, I'm going to do something that maybe is not so good for a while. I remember this happened, a colleague was using pore network models to look at porous media. So why are you going to use pore network models? They can't show you anything. Well, now pore network models are a pretty useful tool in trying to figure out the behavior of systems and how they go along. The problem is that we have this critical interval here where people can throw all kinds of stones and say, oh, you're doing stuff, it's not any good, it doesn't work as well as what we have, it's never going to work. And somehow the research has to be sustained through these critical intervals if we're going to make changes. And it requires that we be courageous enough to stay the course if we're working on something that we know to be useful. So in addressing many problems, a path of change that sustains an established avenue of investigation can be an appropriate way to go. We don't throw out everything and say we always have to do things differently. When we have useful disruptions, they're based on incorporating aspects of important emerging technologies into the model. We have computer abilities that we didn't have before. We have the ability to image at very high resolution that we didn't have before. We need to make ways to incorporate that into our models, even if it requires us to back off for a little while. The disruptive innovations often result in worse model performance over a critical interval of time. And that's not a reason to discount something, the fact that you have a degradation. Disruptive innovations can become a new standard if they're allowed to mature. That finite element stuff I showed you took 17 years to get to where it was kind of competitive. Sustaining a disruptive innovation over a critical interval can be a scientific challenge because people will not say that the work is worthy to be published or funded. It can be a political challenge because people will try and set up programs such that this work cannot be supported because it threatens what they are doing and they don't want that threat there. And it can be a financial challenge because it's hard to do research without any financial support for students. So it's something that journal editors, reviewers, and funding agencies have to be very careful about. And they have to develop approaches that don't just that don't just suppress something that they don't want to see. And it's a difficult task. I think it's the really tough part about editing, is to know the difference between something which is wrong and something which could develop and become really an important element in improving our modeling abilities. So there's this quote that the development of computer technology has not removed the necessity for theoretical studies based on insight and aimed at deeper understanding. These developments of computing technology often tempt us to ignore the essentials of fundamentals in favor of multi-parameter models of doubtful provenance and relevance. A retrospective contemplation of the careers of Langbein and his contemporaries is useful in reminding us of certain first principles in seeking to make fundamental advances in our discipline. And this was written by Jim Doog, who passed away this past summer, in his really excellent article on the career of Walter Langbein. I was talking to someone yesterday who mentioned that he knew Walter Langbein, and one of his characteristics was that he wanted to know what people were doing, but he wouldn't tell them that what they were doing was wrong. He wanted to give them enough leash to figure it out for themselves, or maybe they would figure out that what they had was something different. And we have to be willing to look at things that are different if we're going to impact our modeling capabilities. So the conclusions that I have about this part are the advances in our modeling tools have been accompanied by increased complexity in the problems that we study. There is reluctance to reconsider. Some of it is active reluctance. People really work hard to suppress new ideas, and some of it just are unwilling to think about it. And that really hinders progress. We have to be open-minded. We have to consider things, see what's going on. Progress is not a monotonic function of time. We have to be willing to understand that our work is going ahead with sometimes we have setbacks, and we can learn a lot in our setbacks. If we're going to impact the trajectory of models, it's really important that computation, theory, and experiments across scales be done collaboratively. We just can't develop better models without looking at these other things as well. We have to have collaboration and cooperation, one of the features that Walter Langbein promoted, and we have to be able to bring our breadth of experiences in order to be able to advance things well. So I would like to make some acknowledgements. Acknowledgements are often left at the end because they're unimportant, but this business of collaboration and cooperation is really not something that should be overlooked. And I've had a long career, and I've had a number of really great co-authors, people that some of them I don't agree with anymore, but that's okay. It's been through the disagreements that we've learned a lot together. And I have been, you'll see a lot of names of people that you know. I've been really fortunate to have encountered some really great people. It's not possible to just do work on our own. So these are co-authors. There are many other people, some students, undergraduate students that have asked questions. They always say, I have an easy question, and I always hate those questions. But that they cause you to think, cause you to learn, and I'm grateful to all of these people for their contributions. I also have, in modeling, we have colleagues, and we have model colleagues that help us to advance modeling. And these are people that have been models for me, people that have really been great people to have in my life as colleagues and friends. I have them in alphabetical order. Steve Burgess was the editor of WRR when I first became aware of WRR. He was a great editor. He set the standard for editing that journal. He has an encyclopedic knowledge of the literature. He always is encouraging, always, to try and get people to excel, and he's a great help, someone that really is a model for advancing our profession. Casey Miller is my colleague at North Carolina. It's really great when you have someone next door that you can work with. We've had a lot of laughs and a lot of hard thought about trying to get TCAT to work. It's been a really rewarding part of my career. George Pinder is my first colleague. I met him when I was finishing up my PhD, and he has always been a great colleague, someone I can count on, and I've been fortunate to work with him for so long. Laura Parak-Nolte is the consummate professional. She is engaged in her work. She always has probing questions, and yet she always has time to be a helpful colleague. And it's a wonderful part of my professional life. And if you folks meet these people, and also Andy Thompson, who was one of my students and who sort of stays in the background. He always is there to review things for people. He's probably reviewed most of your papers, or reviewed a paper for most of you. He is always willing to give advice and stand up for people. He has a dissertation that he finished, which I think is still a gold mine that hasn't been tapped into. These are great people. And I hope that all of you have these kinds of colleagues in your life. They will make your research productive. It will make it possible for you to advance in your modeling work or in your experimental work or your field work. And we will all, as hydrologists, be much better for it. So thank you for coming, and I'm done.
Well, thank you very much, Bill, for a very stimulating lecture. We have time for a few questions. I do want to say that I'm actually thankful that perhaps we didn't give you as much guidance as we might have and left you to determine what you would like to say rather than trying to constrain you in any way. Excellent lecture. So if there are questions, could I please ask that you use the mics? And I'll also say it's a little difficult to see out there with the lights up here, so. I have one, and I see John Shockey sitting over here, and I don't want to implicate John, but I think you'll understand the question, which maybe is more of a comment. I was really intrigued by the comments on sort of integrating up from the micro scale to try to understand the macro scale. And, you know, we have a whole class of, you know, with rainfall runoff models, but more generally they're land surface models, and they're sort of important because they're what are in all the weather prediction and climate models. And you know, there's really no, I'll probably get some disagreement on this, but there's really no link to the micro scale and the way we parameterize things. We just haven't made a lot of progress there. Any thoughts on why, I mean, you come out of more of the subsurface discipline. People who've thought about surface water haven't seemed to have made that connection very well. Sort of loaded question, but.
Yeah, SIVA. I think SIVA has worked to make that connection. Is that right, SIVA? Yeah. So part of the problem is, as I mentioned, when you go from the micro scale to a larger scale, you lose the ability to have meaningful intensive variables as the scale gets larger. So when you go all the way up to a watershed scale, the variables become more difficult to define, and their use as driving forces for processes becomes more difficult to incorporate. So I would presume that that's part of the answer, but maybe when Siva speaks to us later on, he can tell us what the real answer is.
Yes, I would like to compliment you on a very beautiful lecture.
Thank
It
you.
reminds us that we have to look across disciplines, regardless where we are, to deal with things like the hydrological cycle, climate, and what have you. I like to think of the atmosphere as always in a state of perpetual disequilibrium at all scales, and that leads us into the issue of nonlinearity. I just point out that in some ways one of the most important things in the global climate change thing is to be able to solve that hydrological dimension of this system. You didn't touch on that so much, but would you want to comment on that?
I didn't hear too well.
Well, the atmosphere, Earth system is in a state of perpetual disequilibrium at all scales.
Right.
Nonlinearity becomes very important. And we do know we can deal with these various processes of entropy, irreversibility, reversibility, etc. But the water vapor and the hydrological cycle sits in the center of that in determining, call it regional climate change, even calling it global climate change. Do you have any advice on that issue? I mean, yes, you've talked about various scales, but how are we going to relate all this together in terms of models? They don't do that well on the hydrological dimensions. That's my view, at least.
Yeah, I happen to, well, I don't know much about doing things at that scale. I happen to believe that when we do this work, we can think that we're coming up with equations that solve everything. I don't believe that the deterministic equations are going to be the ones that end up winning the day in the end. There's going to have to be some stochastics built on top of them. But the stochastic aspects have to be built on sound deterministic equations. And I think that this approach will lead us to sound deterministic equations. The problems we have deal with parameterizations, identifying variables at the large scale. How do we want to average things like temperature and pressure? And we have to tie all of that together. It's an enormous task. It's going to require people with a whole variety of backgrounds to address effectively.
I couldn't agree more that the statistical aspects of thermodynamics and the deterministic, we have a ways to go to be able to deal with that in models.
Yeah, I think so.
Hi. Hi. Steve, you want to? Bill, I'm over here.
Oh, there you are. Hi, Mary.
I think what you're doing is really exciting. What I would like, I guess I'd like to kind of challenge you that it seems like you're far enough along that there could be some perhaps simulation results produced to really clearly show how much difference this could make and how much clearer some circumstances could be for simulation. So it's really just kind of a comment on a challenge.
Well, thanks, Mary. You've always been a challenge.
Oh, thank you, Bill.
Yeah. Mary was a student in one of my classes many years ago. More years for me than for Mary. I agree with you. It's time to start doing the simulations. And Casey and I have discussed this, that this stuff will really be much better received once we show how things are working in the simulations. I do have a colleague in Italy, Bernard Schreffler, who I've done some work with, who I have these references, I should go through them. He's done some simulations involving concrete and the drying of concrete and is able to show that he gets a good match with the stress tensor that's never been obtained before. But yeah, we have to start doing the simulation. It's really hard, and if anyone out there is really willing to try and take these equations and start doing the simulations, I would really welcome the collaboration. It would be fine. Thank you for your comment.
Just behind you here.
Bill, I want to compliment you on an extremely clearly presented lecture of a very difficult material. And unless you were so good in presenting it so clearly, I probably could not make the following comment. And my comment is that reductionist approaches of the kind that you described to us this morning are, in my opinion, extremely useful when you have a situation in which you can separate the scales. Mm-hmm. So if you consider the porous medium to have a well-defined scale, and by the way, a problem I have with this REV concept is that different quantities would have different REVs defined in the way that you have. And so I usually find it not so useful for that, among several other reasons. But it does become perhaps useful if you're dealing with quantities that can all be associated with a given scale, and all other scales are very different from the one that you're dealing with. Then averaging makes sense to me. The problem that I think we all face in hydrology, environmental, and earth sciences in the most general sense is that we live in a world in which there is a multitude of scales which evolve from the smallest to the largest. And separation of scales is an extremely rare possibility. It may happen here, it may happen there. You may have an aquifer that perhaps you can claim is homogeneous, such that, for example, it has a certain correlation scale that is small compared to the size of the aquifer, and then, yes, perhaps averaging on that scale. And it doesn't matter if you start from the microscopic or do it on a microscopic scale. Makes sense. But the problem and the challenge, I think, is going to be to deal with evolutions of scales, a world in which scales evolve, and it's very, very rare to be able to separate them. So the other problem I have with the reductionist approach is that it disregards the possibility that things just happen differently on different scales in terms of processes. As you go from the small to the larger, phenomena come into play which might not have come into play on the smaller scales at which you have decided to do the averaging. And so I do not believe that what we see on any given scale is just the sum of all the phenomena and variables and whatever else you have on the smaller scale. Something new comes into being. And unless we are aware of that, we are in a danger of trying to understand flows through fractured rocks by mapping out the details of what happens inside each fracture and inside each channel. I don't believe in that.
Okay. Shlomo always prefaces a really tough question with a nice compliment and then zap. But anyway, that's what makes him a great colleague. He has great questions. I think that there's a couple of things. I would agree this business of separation of scale is one that can be argued for a long time. There are ways to include different scales in averaged equations, but then there's a need to try and identify those scales. And we're working at this point, assuming the scales can be separated, trying to make some headway on some processes that we think we can model with this approach. I don't believe that any method is going to be satisfactory to handle all problems. I think that the fact that when we average things up, we are more careful in keeping track of these smaller scale terms that come into play and don't just lump them in at larger scale, at larger scales. It gives us a chance to come up with some improved descriptions of the physics. I also really believe very strongly that the best way to make progress is to have different approaches, such as the kind of work that Shlomo's doing and other people are doing, and what we're doing, and to try and make these things move, see where they intersect. Because if they're right, they'll intersect. If something is wrong, they won't intersect in the end. But it's the need to tie all of these things together which is going to lead to the progress. That's about it.
John, I think you were next.
Bill, I really enjoyed your talk.
Thank you.
I wish I could do that kind of work myself and could understand all the important details and aspects of what it takes to relate the mathematics of the physics together. I've been involved in hydrology modeling at a macro scale, and I would love us to be able to explain the dynamics of a hydrologic system in a lot more physically meaningful way than we do today. One of the reasons that I think we do what we do is because we don't know, and in my opinion can't know, what's below the surface in the detail that it might take to explain the dynamics of the system. And so we tend to create phenomenologically based parameterizations of the systems, and then we tend to calibrate those models with some data to make them work. And it would be nice to know what else we might do there. But the question that I have is, to what extent does, in fact, to me, it's amazing that we can do anything in hydrology because we can't see what's underneath the surface. And so to what degree does not knowing what's down there affect our ability to model these systems, no matter how we do it? And how does that relate to the approach that you're proposing that we do with the scaling?
Well, the first comment that I have is when I started this kind of work, when I started working in hydrology, my background was as a chemical engineer, and I didn't have hydrology. And I was told that it was easier to model the subsurface than the surface because the flows are slower. And I've come to realize that I think I agree with you that the heterogeneities in the subsurface, the lack of knowledge of what is there, really makes it a very, very difficult problem. And it's why there has to be some stochastic approaches that come into play to help describe these.
So, Steve, I think we'll...
This is more by way of a comment. Bill, thank you for a superb lecture.
Oh, thank you, Steve.
Thank you for also highlighting aspects of Walter. Walter Langbein was a giant. You think about the journal that we saw, Old Treasure. It was Walter and Alan Canesa, resource economist, who started that journal in 1964. I commend to everybody, keeping in mind that Jenny says we're on record, I commend to everybody to read the first issue of that journal. I followed Alan Fries as editor for Physical Sciences, and Alan said to me, and this is keeping with your talk, he said Walter gave him one piece of advice when he took over the journal, and Alan referred to this as the Langbein doctrine. Something submitted may be wrong, we may not be sure, we may question it, but I recommend you publish it because it may cause people to think very, very carefully. So thank you for raising that, and if everybody in this community gets that clear in their minds, we'll all benefit.
Thank you, Steve.
Thank you, Steve. And with that, I think we'll bring the lecture to a close. Thank you again, Bill. The luncheon commences at 12:30 over at the Intercontinental Grand Ballrooms A to C, I believe. I hope to see all of you there. Thank you again.
Thank you.
Thanks. Excellent. Very nice talk.
Thanks.
Sorry if we didn't give you a lot of guidance.